myself, Dr. Preeti Jagwani. I am from Department of Computer Science, Aribhat College, University of Delhi. So in this lecture series, today's topic is about greedy algorithm, and we'll also look into one of the applications of greedy algorithm, which is fractional knapsack. In my previous lecture, we have looked into Huffman coding, which was also an area where greedy algorithm is being used, and now today we are going to explore more about this. So basically, if we talk about greedy technique or greedy algorithm or greedy algorithm design paradigm or something of that sort, so till now we have seen so many paradigms for designing algorithm which are going to be the solution for different problems. So what are those paradigms? We have divide and conquer, we have dynamic programming, we have greedy algorithms, we have iterative algorithms, and so on and so forth. So greedy algorithm is presently the topic of we can say discussion which we are going with. Greedy algorithm, if we look into this technique into detail, the first thing which comes up is this is used to solve the optimization problems. So is dynamic programming. So both greedy algorithms or greedy techniques and dynamic programming both are used to solve optimization problems, but yes, there are differences in the problems which are being tackled by dynamic programming or which can be tackled by greedy algorithms. Now if I am talking about dynamic programming, the first thing which comes up in our mind is about the optimal substructure of the program. So here also let me mention that greedy, all those problems which can be solved using greedy also exhibit optimal substructure. What actually is optimal substructure? If you are not able to recall, we can have a look into it in a short while. So greedy, when we say they are simple and straightforward algorithms. Why I am saying that as simple and straightforward, I will just explain soon. Now, but they are short sighted in their approach. Short sighted in their approach, that means they just do not look at the global minimum, they are satisfied with the local minimum, and at every step by looking the best solution in the local domain, they are going to build, or they claim to build, a global optimal solution. So greedy algorithm, as I told you, is similar to a dynamic programming algorithm, but the difference is that the solution to the sub problems do not have to be known at each stage, and because of this reason also they are known as short sighted in their approach. So greedy algorithm is kind of short sighted as compared to DP. DP looks into the global optimal thing, while the greedy looks into the local optimal thing. Also it is used to solve the optimization problems. Now when I am saying optimization problems, what kind of problems I am referring to? An optimization problem is the one in which the idea is not just to find any solution, but the best solution, because we need to optimize the solution, and hence the name optimization problem. So the optimization problem is the one in which you want to find not just a solution, but the best solution. Greedy algorithm sometimes works well for optimization problems as well. Because greedy algorithm, if we look into detail, it works in phases. Phases as in at each phase you are going to take the best which you can get right now. So when I am saying right now, again I am referring to the local optimum without recording of picking it without looking into the future consequences of picking it. So if it is a solution which is a local optimal, we are going to take it. This may hamper our total solution in global thing. So without looking into the future consequences, the best which is available right now is going to be picked up, and so that means we are choosing a local optimum at each step, and ultimately we are in a hope, and it happens also that we end up in a global optimal. So basically, if we are going to maintain, or if we are going to, if we want to construct the solution in an optimal way, we need to maintain two sets. One set of sets which is being consisting of, which consist of having the items chosen, and another one which is having the items which are not chosen, or we can say rejected one. As I have told you that greedy algorithms are going to make good local choices in the hope that they are going to result in an optimal solution, and we can say also the feasible solutions. So in short, if we say characteristics and features of this greedy algorithms is they are going to maintain two sets, one set for chosen items, one set for rejected items, and by kind of cumulative, or by accumulating the good local choices, we are in a hope, or we can say the greedy algorithm results in an optimal and kind of we can say feasible solution as well. Now, one thing which is very important as far as greedy algorithm is concerned is the term greedy property. Greedy property is something that says a globally optimal solution can be arrived at by making a locally optimal choice. So basically your greedy property is kind of we can say, or your greedy choice we can say, is having two properties within itself. One is the optimal substructure, another one is the greedy choice property. So greedy choice property says whatever best available you have right now, just pick it up, and then we will be able to construct a globally optimal solution. And the second term, which I told you also in the inception of the lecture, that optimal substructure, this is something which is common between greedy and dynamic programming. So if you don't recall the optimal substructure says an optimal global solution contains the optimal solution of all its sub problems. So basically your problem is your main or overall problem is having so many sub problems, and an optimal global solution contains the optimal solution of all its sub problems. And at every point of time we are being greedy in choosing the next step towards the solution. How we are being greedy? That means we are choosing the locally optimal solution, whatever is available best. So the problems which are going to exhibit the greedy choice property, that means whenever for we can say for coining the solution we need to make a choice, we will be picking the best available and making a locally optimal choice in hope of getting a globally optimal solution. So basically this is what kind of the whole bottom line we can say, or the whole agenda of our greedy property is. Greedy strategy says, as I have told you, that go with the available best. Now greedy strategy is something when we also need to prove that whenever there is a choice to make, one of the optimal choices is the greedy choice. Therefore, it is always safe to make greedy choice. So that means we can say, let us say we are having two solutions. One solution is having named as A, another solution is named as B. It is always safe to make the greedy choice and then coin the solution. Let us say we are making the solution A with the help of our greedy choice, then we can also simply prove that the greedy choice always remains ahead of other solution, which is let us say B. So for example, let us say we are looking for a path from one point to another point. Let us say from P1 to P2 we are looking for a road distance, minimum road distance, and there are so many we can say stopovers in between. So if we are choosing a stopover which is longer than the available one, or the shortest, we are not choosing the shortest one, then cumulatively we will not be able to end up at a solution or at the path which is the least or which is the smallest one. So, it is always a better idea, or it is always safe to make a greedy choice. And also we can show that all but one of the sub problems resulting from the greedy choice are empty. So, this is basically here in this way we are going to coin the whole solution. Now, if we talk about what all problems or which all applications are there in which you are going to use greedy. So, if we want to name them, there can be many. So, one is activity selection problem that we are going to look into now. Then we have our fractional knapsack. Now, fractional knapsack is altogether different from 0-1 knapsack. So, in fractional knapsack obviously we are going to use greedy, but for 0-1 knapsack dynamic programming is the solution. Apart from that, I have told you activity selection problem. Then we have also seen Huffman coding in our last lecture, which was also based on greedy. Then coin change problem is something which is based on greedy. Then in minimum spanning trees, if we talk about, we have two methods which are Prim's minimum spanning tree method and Kruskal's minimum spanning tree method. Both are based on greedy choice. Then we have shortest path problems. All those problems, as I was naming them, are based on greedy choice. That means they are going to pick the available best choice, and then they will be look into the next phase of their solution. So, in a try to understand this whole theory of greedy techniques, let us begin with a problem which is known as activity selection problem. Now, let us try to first understand that what is this activity selection problem, what is going to be the input, what is going to be the output, and then we will try to coin a structure which is based on this optimal substructure term, and then we will use that optimal substructure in order to find a greedy solution to this activity selection problem. Now, activity selection problem says that let us say there is a set S, and this set S is having a number of activities, let us say n activities. So, all these activities are kind of named as A1, A2 till AN, where Si is the start time of activity I and Fi is the finishing time of activity I. So, for example, if I am talking about S3 and F3, so that means S3 is the starting time of activity of third activity, which is A3, and F3 is the finishing time of the activity 3, which is A3. Now, this was the input given in activity selection problem. What do we need to do, or what is expected from the algorithm is to find a subset A of maximum number of compatible activities. Now, what are those compatible activities? So, we can say two activities are compatible if their intervals do not overlap. Now, in order to understand this activity selection problem, let us take a very simple example. So, simple example is of, let us say we have a lecture theatre and we want to assign this lecture theatre to number of we can say departments. So, a lecture theatre in a college, commerce department is asking for it on a particular day obviously. So, as maths department is asking, and computer science is having a request, and Hindi and English are having request. So, what do we need to do? We need to choose a subset A of all these activities. So, activities here are your Hindi department, your the request from the various departments. And what do we need to choose? We need to choose a subset A of maximum number of compatible activities. Now, let us say the lecture for computer science, or for the requirement of computer science for that lecture theatre is from morning 9 to 11, and Hindi has given a request from 10:30 to 12. So, both these activities are kind of non-compatible activities because their intervals are overlapping. So, from 9 to 11 if CS is asking, then we cannot allow any other department to start their lecture from 10:30 on the same space. So that means these two activities are non-compatible. So what do we need to do here? We need to find compatible activities. That means they should not overlap, and we want to satisfy maximum number of requests. So we can start from, let's say, 9, we can go till 5. So 9 to 11 is one, and then maybe 11 to 12:30 is another, then from 12:30 to 3:30 is next, and so on and so forth. So input is a set of activities with their start time and finish time, and output is a subset A of maximum number of compatible activities. That means whose intervals are non-overlapping. So in order to just to see it in a very formal manner, let us have this figure on the screen. So here you can see I have just drawn the lines. So in each and every row or in each and every line, if you can see, these activities are considered as compatible. So in the first line I am having 2 activities, they are compatible, interval is not overlapping. But if I am saying I am going to choose the first one from the first line and the second one from the second line, so that is not possible because these two are kind of overlapping. So these are non-compatible activities. So each and every row, if you can see, all the rows in these lines are compatible. So the first line 2 activities are compatible, then the second line 2 activities are compatible, and in the last line, the bottom line, the 3 activities presented are compatible. So if we want to maximize the number of compatible activities, the idea is we are going to choose the last one, which is the kind of third one, we can say. So that is the schedule we should choose. So this is what your kind of, we can say, an activity selection problem is. Now after understanding this activity selection problem, if we look into how are we going to kind of formalize it, what kind of optimal substructure is present in this problem, let us see that. So optimal substructure, in order to understand this optimal substructure with reference to this particular problem, let us assume that these activities are sorted by their finishing times. So F1 is the first one to be kind of finished, then there is F2 till Fn. And let us say an optimal solution includes a particular activity, let us say AK. So if I am going to choose this activity to be included in my optimal solution and the activity is AK, now I am having 2 sub problems in hand. So the first is we need to select A1 to AK minus 1 activities which are compatible with one another and that finish before this AK is starting. So that means the 2 sub problem is selection from A1 to AK minus 1 activities which are compatible with one another and that finish before AK starts. That means they should be compatible with AK. And the next problem is selecting from AK plus 1 to AN activities which are compatible with one another and that starts after AK finishes. So that means on both sides of AK, if you want to visualize or if you can visualize that in the form of a line, so there is an activity AK. So whatever is left on the AK, we need to choose that. Whatever is right on the AK, which is after finishing the AK, we need to pick compatible activities from those also. But the activities which are either starting or finishing within the duration of AK, we are not going to kind of, we can say, we will not be able to take them up, we will not be able to select them up. So for this we need to build a recursive solution. So the solution says, let us say S of ij is the subset of activities in A that starts after AI finishes and finish before AJ starts. That means we can say kind of compatible activities. and the subproblem says we need to select maximum number of mutually compatible activities from this set S of ij, which is the subset of activities in A. So, in order to build this recursive solution, we can say that, let us say C of ij is equals to the size of maximum size subset of mutually compatible activities in this S of ij. Now, this C of ij is going to be equals to 0 if S of ij is equals to 5. That means, if there is no activity. So, here as I have told you that we are going to build a recursive solution. So, in recursive solution we also need to take care of the base case. So, this is going to be our base case. If S of ij is equals to 5, then size of this C of ij is going to be 0, or this size of C of ij is going to be max of C of ik plus C of kj plus 1 if S of ij is not equals to 5, where I is less than k and k is less than j. So, this is the situation where we have already picked up A of k. So, we are going to now pick the maximum size mutually compatible activities, which is max of C of ik plus C of kj plus 1 for that which we have already chosen. So, in this way we are going to build a kind of, we can say, recursive solution. And the greedy choice property, here says the optimal solution to this subproblem S of ij is include the activity with the smallest finishing time in set S of ij. So, for example, I am talking about one lecture which is starting from 9 and ending up at 10, and this is the first one to get finished. So, the smallest finishing time, we have already arranged our activities in the order of their finishing times. So, the smallest finishing time we are going to pick, and whatever non-compatible activities are there which are clashing in a way in interval with that with the activity chosen, we will be taking them out of the domain. We are not going to consider that. So, the greedy choice we need to make without going into solution of the subproblem first, without going into evaluation of those subproblem. First of all, we need to make greedy choice. So, here in this activity selection problem, our greedy choice is you need to pick the activity with the smallest finish time, and then we need to solve the subproblems that are going to ensure ensure a solution as a result of making this greedy choice, and then we will combine the greedy choice and solution to those subproblems. If we try to look it within in the form of an algorithm, we have a recursive solution here. Here a recursive activity selector with your S is the set, then F is the finishing time, then activities I and J are there. So, first of all we are going to say that we are going to pick, let us say, one particular activity, and if my M, which is I plus 1, is less than J and S of M is less than F of I am going to increment one particular activity into that. So, M is M plus 1, and if M is less than J, then we need to return A of M union a recursive activity selector S comma F comma M comma J, as we will be returning phi. So, here basically if you look into this recursive algorithm, what are we going to do? We are picking the first activity with the least finishing time, and we are discarding, we are rejecting all the activities which are kind of non-compatible with it, and then we will be looking into all other activities which are left in the set. and then we keep on building this solution. We will next pick the next activity which is compatible with this, and then we will discard all the non-compatible ones. Then we will select a pick the one with the least finishing time. So, this is in this way we are going to kind of, we can say, build up the solution on the basis of our greedy choice. So, we will be making a greedy choice, solving it in the top down approach, and the greedy choice which we have made is select the activities by their finishing time. And the typical steps here are we need to take these activities, pick them up, discard the non-optimal ones. So, in this way in this lecture we have seen whatever we are going to what applications we can solve with greedy technique, and we have taken the example of one particular technique which is your activity selection problem, and we have given a broad level solution to this activity selection problem using our greedy choice. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.